All right, everyone, we're going to recap how to solve exponentials of all types. We did these in various stages, but we're going to do them all together and kind of hopefully get an idea of how they're all linked together. So remember, the most ideal situation is if we had the same base on both sides of the equal sign or the inequality sign. All we had to do was say our exponents must be equal or our exponents must be unequal in the same way. So for these two problems, because our base is the same, both of them in the first one are 2, all I have to do is say 4x equals 32 and x must equal 8. It's that simple. All of that is predicated on the fact that our bases are the same. Again, over here on number 2, 3 is the same as 3. Those are my bases, which means that my exponents must be unequal. See, I have an inequality symbol here in the same manner. So now I distribute on this side. I move my x's to the same side by subtracting 2. And I have x is less than 8, and if I were to write that in interval notation, it would be parenthesis negative infinity to 8 parenthesis. Again, this side is parenthesis because this is exclusive. In the real world, our bases aren't always going to be the same. So our first strategy is we'll try and make them the same. So it's helpful if you know powers of bases. For instance, if you know powers of 7. 7 to the first is 7. 7 squared is 49. So therefore, I can rewrite this 49 as 7 squared and then raised to that exponent of x plus 5 is going to be greater than 7 raised to the exponent of 8x minus 6. Now I just use my exponents. That's all I'm interested in. And I get 2x plus 10 when I distribute is greater than 8x minus 6. And then I get negative 6x is greater than negative 16. X is less than, because I'm dividing by a negative, that reduces to 8 over 3. Okay, and you can write that in interval notation as well. This one, notice that I have a fraction here, okay? So look at this hint. It says rewrite fractions as the other base with a negative exponent. Well, 625 is 5 to the negative 4. So I'm just going to rewrite this. 5 to the 3 minus 2x has to equal 5 to the negative 4. You have to have some grace with me on this. What I'm writing on is sometimes it's difficult. So this says 3 minus 2x has to equal negative 4. Negative 2x has to equal negative 7. X has to equal 7 halves or 3.5. Okay? So far, so good. Now, what happens if in the real world, and this happens a lot, the two bases can't be forced to be the same? Well, this is when we learned that we can apply a log to both sides. You're actually taking the log of both sides. And in doing that, you can use the properties of exponents and the rules of logs, and you can solve for that variable. So let's do a couple of these examples. There's 3 of them here, so hopefully we can get them all to fit. All right. Look at base 2 and base 17. As hard as I might try, I can't get them to be the same. So I'm going to apply the log log to both sides. I could apply ln to both sides. It's not going to make any difference. However, you want to notice that if one of your bases is e, you always want to use ln. Here I'm going to use log For those of you who'd like, you can try using ln and see if you get the same answer. So I have log base 10 of 2 to the x plus 2 is less than log base 10 of 17. I move my exponent forward. Notice that I put parentheses around that x plus 2. And now I'm going to divide both sides by log 2. And that gives me over here log 17 divided by log 2. Again, we're in base 10 here. And now x is less than log base 17 divided by log 2 minus 2. And when you put that into your calculator, you get a nice decimal of x is less than 2.0875. Now, up here, notice up here, I could have distributed. I would have got the exact same answer, all right? Hopefully you can read that. I'm trying. All right, this next one is base E and base 16. They're different. Cannot get to the same base, so I'm going to apply ln to both sides. And notice that I applied to ln 16. All right, and then I bring my power down. Now the thing about lne, that is one of our properties that we want to just have at our fingertips and know what to do with. Sorry, my pen is really misbehaving. I am so sorry. 16, that's an ln. Okay, this always simplifies to 1. So what's left over here is 3x plus 2 is equal to ln of 16. So 3x is equal to ln 16 minus 2, and x is equal to ln 16 minus 2. Now when you put that in your calculator, remember to close off that parenthesis after 16. Minus 2, hit return, and then divide by 3, and you get x is approximately equal to 0.2575. All right? And then our final example that we have here is I have to isolate this e to the x before I apply ln to both sides. So I'm going to add 7 to both sides, plus 7 plus 7. So I get e to the 3x is equal to 19. Now I apply ln to both sides. ln e to the 3x is equal to ln of 19. And that means 3x times ln of e is equal to ln of 19. Sorry about that. ln 19. And then this becomes 1. So 3x equals ln 19. X equals ln 19 divided by 3. And when you put that in your calculator, you get a nice decimal of 0.9815. All right? Okay. Now, there's a couple of problems that I want you to try before we start talking about logs. So I'm going to end this video here and start a new one. And then you can check these on the last 2 slides of your sheet. Thanks for listening.